Hello, here is once more we pursue our lessons on integration, and this lesson in fact is our last lesson in the course, and it concerns the application of integral. Now, like we did in case of differentiation, we devoted one lesson to the application of differentiation. We should as well devote one whole lesson to the application of the integral. Now, integrals appear in all variety of applications. There is no one single science that you can single out without resorting to integrals. Integrals, in other words, they appear in all sorts of sciences. Now, in this lesson, we shall be speaking about where the applications of integration appear, and then the most important application of integration actually is the calculation of areas, and then finally we talk about some approximate integration, because not all of the integrals we can calculate, so we have to resort to ways to approximate integrals. Now, to speak about where do integrals exist, as I said, they appear in all varieties of applications. The most important of which, not really the most important, but one which really contains integration all the time, is when you have differential equation. And the meaning of differential equation is the algebraic equation. For example, you seek to determine a value x which satisfies an equation, whereas in differential equations you have here a function y of x, and you seek to calculate this function. In other words, to solve these particular equation here, the solution of which is not a number, but it is a function of y in terms of x. And here, this is, for example, the second law of Newton, the solution of which gives you the distance as a function of time of which, for example, a certain body travels. Now, one of the applications, for example, here is to calculate the sum of series. Remember, in our lesson of series, we talk about the convergence of series, but we didn't find ways to calculate the sum of these series. Here is one of the application, is to calculate the sum of this series. For example, here you have a series of x, and this power series, there is a radius of convergence. Those value of x, in fact, which is the modulus of x, is less than 1/3. And how do you know this? Here it is easy, because when you want to sum up this series, what you do is that you, for example, you integrate it. Suppose you want to sum up the series. When you integrate it, you get a geometric series. Now, this geometric series has the first term is equal to 3x, and the ratio is equal to 3x. So you have, we said before that for geometric series, if the ratio is the modulus of the ratio is less than 1, then the series converges. And this series here, you have the ratio is equal to 3x, so the region of convergence is given by the modulus 3x less than 1, or x modulus x is less than 1/3, and this is the condition imposed in order to obtain a convergence of this series. Now, this series here, the sum of which is easy to calculate. Why? Because infinite geometric series, the sum is equal to the first term, which is 3x divided by 1 minus the ratio, which is 1 minus 3x, and here you get directly the sum of the series. And when you, after you calculate the sum of this series, what you do therefore is to differentiate again the series, this sum, to obtain the original series. And of course, the original series have the same ratio, have the same intervals of convergence, so again it's convergent for modulus x less than 1/3. So what you do here is that you integrate it, you obtain the sum, because you know that the sum of a geometric series, and then you differentiate again to obtain you differentiate the sum to obtain the sum of the original series. This is one application of integrals. Again, another applications, and this is very common applications in economics. We know that in economics, for example, you have the price versus the goods produced, Q, or the quantity produced. And we spoke before about the elasticity of demand, and you said the elasticity of demand in economics, it means that this is the ratio between the percentage change in the quantity demanded divided by the percentage change in the price, and usually it's sort of a curve like that. Why? Because the higher the price, the less the quantity demanded, and when the price falls, you have a higher demand for these goods. And there is another curve which which is called the supply. This is called the demand curve. And this is the supply curve. The supply curve is that of the producer. The producer, of course, is encouraged to produce, to deliver more goods to the market when he finds that the price increases. While when the price falls, he is not very much interested to produce more goods. So here you have what is called an equilibrium position here, and equilibrium price P naught. At this equilibrium price, this is it gives you the relationship between the supply curve and the demand curve, and this stability point, or the equilibrium point, is the point at which both the consumer and the producer would be willing, one to consume the goods at this particular price, and the other one is to produce the goods at this price. And then if you wish to calculate, for example, here this quantity here is called the consumer surplus. Why? Because the consumer actually would benefit from because these consumers are willing to pay more for the goods, yet they are gaining from the fact that they are going to consume their goods at a value of price P naught less than the price they are willing to pay. So actually, if you know the relation between P and Q, suppose for example you have P, the price in terms of the quantity, the difference between P minus P naught dq, because actually this is the difference between the price they are willing to pay and the price they are really paying. The difference between the two is times dq is the consumer money they are willing, they are going really to or they are willing to pay, yet they are gaining from the lower price, which is the equilibrium price. And if you integrate this, what you get is called the consumer surplus. Of course, there is another curve here, which is, this is the demand curve, and this is the supplies curve, and this is the equilibrium position here, Q naught, at the particular price P naught, and actually what you have here is the consumer surplus. Of course, coinciding with the consumer surplus, there is also the producer surplus, because yet they are gaining also, because although they are willing to produce their goods at a lower price, they are gaining profit out of producing it at the price P naught. So this is one application, for example, in economics of integration, because you wish to calculate here this area, which is equal to P minus P naught from 0 to Q naught. You integrate this and you get the area, which is the consumer surplus. Again, you may find applications in economics, because we know, for example, in economics there are periods, for example, of growth and another period of recession. This is called recession. And these, for example, one of the applications is that you wish, for example, to apply this is a periodic function, because periods go, they climb and they decline here. And you wish, for example, suppose, for example, this is a modulus function, mod x, for example. And you wish to this is a periodic function, and we know that there is a scientist living in the late 18th century. He said that any periodic function can be represented, like this one, for example, by a series of trigonometric function. Here you have, for example, the sum over 1 over n square times 1 minus cosine n pi times cosine nx pi divided by 2. Now here it tells you what? It tells you that you start, of course, your recession and growth does not follow an absolute value of x, but doesn't matter. Here you have a time going on like this, and then it reduces again. You have a decline. Of course, you can have, for example, a period of tau in which there is a growth in the economy, and another equal, for example, a period when there is a recession, and where there is a recession, and you have a periodic growth and decline always in the economy, and you wish to, for example, represent this kind of behavior by a series of trigonometric functions. Can you do so? Yes, you can, because you can expand, for example, a function of this sort is not exactly the function in economics, but it is more or less the same. And if you expand these functions here, in order to calculate these terms here, you have to rely on integrals. And of course, this you can can, for example, suppose you substitute x equal to 0, and you sum up the term here, what you get some form of series. In other words, this can be, of course, also used in order to obtain sum of series. Again, you may have, for example, what's called the marginal cost of production. In economics, you have the costs over the time here, and you produce a certain, you try to calculate, to exemplify or to seek a behavior between the cost and the time, and this cost varies because at a particular value of time, although the raw materials, for example, cost so and so, after a certain while the raw material may increase. So you have a relation between the costs and the time, and you may wish to calculate, for example, the mean of that cost. What is the mean cost over, for example, 10 years? How you do this? You plot the cost versus time, and then you integrate over 10 years, and you divide by the period of 10 years. And this we saw before, actually, in our last lesson, in the lesson before, when we mentioned the what is called the mean integral form. And we said that you have a continuous function, so the integral of fx dx from a to b divided from b minus a, and is called the f of zeta. In other words, if you integrate the cost over time and you divide by 10 years, you got the mean value of the cost over the years. Not only that, but the theorem, which is the integral mean value theorem, tells you that there is, if you obtain this mean value of the cost, it tells you that there is a point in time where the cost equals to f of zeta. Now, to exemplify this here, suppose, for example, you have, here is, for example, this is, you have a function here, and suppose, for example, function of the cost versus time, and x represent the time. So, for example, what you do is that you integrate, you obtain the whole cost, and then what you do is that you calculate the mean value. So this gives you what? This gives you the mean value of the function. This is another applet that has been devised at Cairo University. If you change the function, for example, this one here, this is the function we started with when we talked about the definite integral. This is the function. It represents a certain relationship. We don't know about it, what kind of relationship it represents, but doesn't matter. Again, here, if you take, for example, 2 points here, and then you wish, and this gives you the integral, in other words, the whole variation of the function over the time. When you integrate it, you got the whole, for example, if this is cost again, so this gives you, and there is a decline, so it gives you the total amount of cost over the years, and when you divide over the interval from this point to that point, what you get is here, you get the mean value of the function. But this is not the only application. In fact, you can have as many applications as you wish. For example, suppose, for example, you wish to calculate volumes. For example, we used the integration to calculate areas, but you may well use it to calculate volumes. Here, for example, what you do is that we can divide the interval from -1. Here you have a circle, for example, and this circle rotates about the x-axis. What you get? You got a sphere, of course. What you do is that we can subdivide the interval from -1 to 1 into many subdivisions, and then what you can let each subdivision rotates about the x-axis like this. Here is what you get. You get a disk, or you get a cylinder. Now what you do, you can allow this cylinder to scan over the whole interval from -1 to 1. So what you do is that you have a whole sphere. And this sphere, when you take the limit, when the number of subdivisions goes to infinity, and this is the idea of Riemann, the norm of the partition tends to 0. What you have here, you have a whole sphere. This is again one other application of integrals. But the number of applications actually are numerous. There is no one single application. Here is a third application. For example, you wish to calculate not volume of integration, but the surface of integration. What you do the same thing. You have here, you subdivide again this region here, this line. When this line rotates about the y-axis, it gets what? You get a cup. How can you obtain the surface area of this cup? You take a piece of element, and then after that you take a particular value. This is here it is. This piece of element of this curve you let it rotate about the y-axis, so you get a piece of area. You calculate first the area of this piece when it rotates, and then what you do, you sum up over the whole integral or the whole region, and you get the area of the cup. In other words, the number of applications, as I said, are varied and they are infinite, and all of them lead you to the applications really of integration. So the application of integration are numerous. But the one application of integration, like the one that we saw in economics, the most important application of integration is how to calculate areas. And to calculate areas, what you have an integral. We go back again to the fundamental theorem. If the function is continuous, if it is not continuous, it doesn't matter. You resort to Riemann integral. So if the function is continuous, as I said before, this is the most important case in which, or situation that you always encounter, whether in economics, in engineering. I remember when I was a student, I was all the time using the fundamental theorem. So here it is, your function, if it is positive, your integral is positive. And if it is the function is negative, in other words, your graph is below the x-axis, what you get, you get a negative value for the integral. Now, for example, here you have a function y is equal to cosine x, and you want to evaluate the integral from 0 to 3 pi by 2. What you get here, you apply the fundamental theorem. The integral cosine is sine. You apply the fundamental theorem and you substitute from 0 to 3 pi by 2, you get minus 1. What is the value of minus 1? This is the value of your integral from the point 0 till the point 3 pi by 2, whereas it's not equal to the area. To the area, you have to calculate the area here, and here, because it is negative, the integral is negative, so you take the positive value of it, or in other words, you take the absolute value, you replace the negative value of the integral here by the positive value, because area cannot be negative, the area can be positive. So actually, if you are interested in the area and not the integral, so whereas the integral is equal to minus 1, the area is different. The area, you have to calculate the area from 0 to pi by 2, and then you calculate again the integral from pi by 2 to 3 pi by 2. Here, what you do is that you substitute for the area from 3 pi by 2 to 3 pi by 2, you replace it. Instead of minus 2, it becomes as area equals to 2. So the whole area now from 0 to 3 pi by 2 as area is equal to 3. So as area, it has the 3 units of area, whereas the integral is equal to the sum of these two, which is equal to minus 1. If the area, now if you have, for example, an area lying between two curves, you have here the curve of y is equal to f of x, whereas here y is equal to g of x, and you wish to calculate the area in between. Of course, the Riemann integral tells you that you have to take the difference between both ordinate, between both y. So here f of x minus g of x, or you can say that the area between the two graphs is equal to the area under the first graph, f of x, minus the area under the second graph. So what you do is that you integrate f of x minus g of x, and you carry out the integral. Here it is. So this is represent the area between the two graphs. Here it is. For example, you want to calculate the area comprised between the two curves. Here you have a straight line, y is equal to x plus 2, and here you have a parabola, y is equal to x squared, and you wish to calculate the area of this region. So what you do is what? Is this is f of x, and this is g of x. So the area is equal to the difference between f of x and g of x, and you integrate between the 2 points here. How can you get these 2 points here? All you have to do is that you solve these two curves together. In other words, you set x squared is equal to x plus 2, or x squared minus x minus 2 equal to 0, and you get the root, and you directly get the result that the roots, you have two roots here. One is at minus 1 and one is at 2. The point 2 here corresponds to y is equal to 4, whereas to point minus 1 here corresponds to y is equal to 1. So you have to carry on the integral between in the closed interval from minus 1 to 2 of what? Of x plus 2 minus x squared. And here it is. The area between the two curves is equal to this. And from minus 1 to 2, and you got 4.5, and you carry out using the fundamental theorem quite easily, and you substitute between the two limits of integration. Now here, you can do the same thing, except that here you have, it's complicated. As a matter of fact, what you can do here is that here is your curve, and here is your straight line. What you can do, you can divide this region into two parts here. You can integrate between these two curves here from this point here to this point, and then you can carry the integral from this point here to the end of the interval here. But it's complicated because you have two different values of function. Here you have to solve y in terms of x. Here you have, for example, x is equal to y squared, so you have here y is equal to square root of x, and here you have minus square root of x. In other words, you have to integrate square root of x minus square root of x dx. But it's better actually to do a different way and then here you have between, you have square root of x and the line which is y is equal to x minus 2 if x is equal to y plus 2. So you can do this here. In other words, here you substitute from x from 0 to 1, and then you carry out the integral of what? Of the square root of x minus 2 dx, which is, as a matter of fact, here from 1 to 4, which is complicated. So the best thing of doing it, instead of dividing the integral into 2, the best thing is that you can take, as a matter of fact, you can take a different line of approach. How? Instead of integrating y dx, and here you are stuck with two regions here and there, you can instead take the strip, horizontal strip. In other words, here you get what? Here you get x1, and here you get x2, and here you get the base. Instead of dx, you get a dy. So instead of calculating the integral of x, y dx, you may use the integral of x dy, which is better. In other words, you integrate the lamina here, this lamina here is the difference between x, this x and this x, and you integrate, you multiply it by the base, which is dy, and this is the area of your strip, and then you integrate from y1 till y2. So what's the value of x here? X is equal to y plus 2, and this x here, and this x here is equal to y squared. So which is greater? This one. So you can put x1, which is y minus 2, minus y squared, and you integrate with respect to the y, and then you integrate from 1 to 1, 2. Here, like this one here. Here you have your curve. Here you have x is equal to y plus 2, and x is equal to y squared. So you subtract y plus 2 minus y squared, which is the length here. This is the length of your strip, times the base, which is dy, and then you integrate from what? From y is equal to minus 1 to y is equal to 2. So you have a different line of approach. Instead of having two integrals, you can have just one simple integral. So this is the first method, as we said. This is the first way we did it. We have two curves in one integral and the other curve on the other integral. So instead of doing this, we can follow a different route. If that instead of integrating y dx, we take a different lamina, a horizontal lamina. Here, this is a vertical lamina, and the other one is an horizontal lamina. You integrate x dy, and actually you get the same. If you calculate these integrals here, you get it. You must obtain also 4.5 as the unit of area. But this is, of course, far better to do. Now, if you have an area between two intersecting graphs, as we said before, the integral could be positive or negative, but the area is always positive. So if you wish to calculate integral, you can just carry on the integral f of x minus g of x if you have two curves. But if you are interested in area, here you find out that here this f is greater than g, while here g is greater than f. So if you calculate from the beginning area, what you can do is that you calculate the integral from a to c, and here you substitute the difference between the two, which is greater f. So you have f minus g, whereas here you have j minus f, and then you carry out the integral from a to c. You have here f of x minus g of x, whereas here you have g of x minus f of x, and you integrate from c to b, and in which case you have here the integral is positive, and here also it is positive, so you don't need to revert or invert the sign of your integration. Here it's like this one here, for example. You have, for example, you want the area between the two curves, x cubed and x squared. Here in this part here, it's x squared, which is greater than x cubed, because we know that when you have the cube of a number, it's greater than the square of the number when the number is less than 1. When it is, greater than 1. But when the number is less than 1, it's x cubed, which is smaller. Why? Because you have, for example, 0.1. When you square it, you get 0.01. And when you take the cube, it's 0.001, which is less. So here, whereas here you have x from 0 to 1, x squared is greater, and from 1 to 2, you have x cubed, which is greater. So what you do in order to obtain the area between the two, here you subtract x squared, which is greater, minus x cubed from 0 to 1, while here you get x cubed minus x squared, because this is greater than 0 from 1 to 2, and you add up the integral with their signs, so you get at the end 3 over 2. Sometimes in all these examples we give, we spoke about Cartesian coordinates. In other words, we follow the fundamental theorem applied to A, B, and we said that the area, you take the lamina as this one here, and you say that the integral is f of x dx from A to V. In other words, you take a lamina of base dx and of height f of x, and you sum up, because what you do actually, you do this. This have the same meaning, and we said this in our introduction lecture, that this constitute the sum and the sigma, and this is why we use this notation for integration, because we are summing. We are summing what? We are summing all these rectangles together. So instead of doing this, we can actually, suppose you want, for example, the area of a circle. How can you do it? Of course, you can, first situation, you can say, for example, that you integrate 1 minus x squared. If you have, for example, a circle of center at the origin, at the point 0 and 0, and of radius is equal to 1. So the integral, the ordinate here is equal to square root of 1 minus square root. So you can calculate the area of the circle using, for example, the integral from minus 1 to 1, and then you multiply by 2 to get the area of the circle, which is equal to pi. This is one way of doing it. But the other way of doing it is that you can divide the circle into circular sectors like this, and each one of them, what's the area of each one, is equal to what? Is equal to the perimeter of, for example, you have a certain disk of radius equal to r, and the thickness of that disk would be what? Would be the circumference 2 pi r times the thickness, which is r, and then you integrate 2 pi r dr from 0 to 1. What you get here, you get pi r squared, and from 0 to 1, so you get pi as well. So this is another way of doing it. In other words, you have a circular disk, and the perimeter is 2 pi r times the r, you get the area of the disk. When you integrate them, when you integrate with respect to r, you get the area of the circle. So there is no one single way of carrying out integral. The idea is to what? Is to get smaller lamina, depending on the way you choose your lamina. Depending on whether you prefer to have it as circular or horizontal, like we have it in the example in which we wanted to calculate the area between y squared, x is equal to y squared, and x is equal to y plus 2. Or you may have it as vertical strips, and you integrate y dx or f of x dx. They all amount to the same. Because, as a matter of fact, what you do is that you integrate and you take the sum, and and when you take the limit, the sum becomes equal to the integral, and you use the notation of the sum, which really represent the integral under, or the area under your region, or the area of your region. And as I said, depending, or the way you prefer to choose your lamina is the way that you proceed again or further on to sum up all these lamina, and you substitute the sum by your integral, and you carry out your integral. Now, sometimes functions are difficult to integrate, and this is why. So we have to finally speak about methods that are used when you have complicated functions. Like, for example, suppose, for example, we have a function of this sort. For example, the integral of the square root of 1 plus x cubed. Now, 1 plus x squared, we know how to do it. But 1 plus x cubed, we don't know how to do it. So these kind of integrals, when you find these sort of integrals and you wish to calculate the integral, instead of calculating exactly using the fundamental theorem, you can resort to what they call approximate ways. So, for example, this way, you want to calculate this integral. What you can do, one of the ways actually, is you can substitute this function by the Maclaurin expansion, or the power into a power series. So here again, we see an application of differentiation and of integration. So if you do this, for example, suppose we can, here we substitute the square root of 1 plus x cubed into this is a Maclaurin series, in other words, Taylor series expanded around the point x equal to 0. You got this series, and you want to carry on the integral here. What you do, you integrate the terms here one by one to obtain this value. Now suppose when you obtain this value, you wish to calculate the error because this is an approximate way of doing it. It's not the exact way. We didn't follow the usual way of using a substitution, for example, and then you carry on to calculate it exactly, to obtain antiderivative. We don't know how to obtain it. So in this kind of integrals, what we do, for example, you can, one of the ways, of course, you can do a Taylor expansion and then integrate it term by term to get, this is actually the result of your integral. But this is approximate one. Why? Because there is a remainder here. You remember when we were talking about Maclaurin expansion, we said that there is a remainder. So what you do, we have to integrate also the remainder. So this remainder, what is the maximum value of this remainder, is equal to 15x squared divided by 16 times the factorial of 4. You integrate the remainder, and when you integrate the remainder, you get the error 3 times 10 to the minus 3. In other words, the value of your integral using Maclaurin expansion, you get an exact value, except there is very small error, and the error is almost negligible. Here the error is equal to what? 3 times 10 to the minus 3, in other words, 3 in 1,000. So what you have actually calculated is almost correct. So this is one way of doing it. Another way of doing it, we said before that the integral is what? The integral, as a matter of fact, is to sum up area of rectangles. Instead of summing rectangles, we can sum up trapezoids. And if you remember in our last lecture, we said that the integral is what? Or the second branch, or the second problem in calculus is to carry on, is to calculate integrals. And we said the best way is to subdivide the region into not rectangles but trapezoids, because they are much accurate to represent the integral. So if you use the trapezoidal rule, now the area is composed of trapezoids like this, and you carry on. What you do is that you sum up the area of these trapezoids, and you come up with a fair approximation of your integrals. Now what you do, we know very well that when you have a trapezoid like this one, for example, this is a trapezoid, the area is equal to what? Equal to twice the sum of the two base times the height here divided by 2, or the mean of the two bases times the height. So here, for example, this is one of the trapezoids between the point I and the point I plus 1 is equal to what? The base h divided by 2 times the sum of the two bases. When you want to calculate the whole area, all you have to do is to sum the whole number, the whole sum, or the sum of all the trapezoids. Here, because each height is represented twice, f1 plus f2 divided by 2, plus f2 plus f3 divided by 2 plus f3. So you find out that the first and the last height is not multiplied by 2, whereas the one in between is multiplied by 2. And here is an expression for the whole area wish to calculate. So what you do, all you have to do is that if you have a function that which you integrate approximately, all you have to do, you subdivide it into equal, for example, some intervals, each of height h, and you calculate the height over the whole domain from A to B, and then you substitute in this expression here to get the overall area. Of course, there will be an error. Why? Because actually the function goes like this, whereas the trapezoid, this is the area of the trapezoid. So actually there is a negligible error. What is the amount of this error? We have to calculate it. You do it what? You do it by expanding the function by Taylor around this point. We shall not be doing it, but you can do it yourself. You can expand the function, your function at any particular value over x, knowing the value of the function here, which is f naught, for example, plus h f dash at naught. This is the Maclaurin expansion about this point here, and then you integrate it, and then you subtract from it the area, the approximate area which you use using your trapezoidal rule, and the difference between the two, you will find it equal to a very small value of this sort here. It's the b minus a, the end point minus the two end points. This is your interval. The length of your interval, cube divided by 12n square. And actually, the more points you take on the interval, you should realize that the more accuracy your approximate integration will be. So we can actually, this is the expression for the error, and we can apply it directly to, for example, evaluating such an integral. You have here, for example, e to the minus x squared, Of course, e to the minus x squared is a composite function of two continuous functions. So this function is continuous, and it can be applied. Actually, it has an antiderivative, but we don't know how to calculate this antiderivative in the form of elementary functions. So what we can do, we shall do it using an approximate integration, and we chose to do it by the trapezoidal rule. So what you do, you decompose it into the interval from -2 to 0 into, for example, 10 regions, and then we want actually to determine the number of points required so that the error does not exceed, for example, 5 10 to the minus 5. So here, again, what we do is that we at this part, we take 10 points from -2 till 0, and we calculate the heights of the function at these particular values, and then we substitute into the expression that we have to calculate the area. Here it is. This is b minus a. This is 0 minus -2 divided by 10. This is h. This is the base of each subdivision. Divided by 2, this is h by 2, times the first height plus the last height plus twice the ones in between, and this is the approximate area that you should have. Now, if you want to calculate the error, this is the error. The error is equal to what? Is equal to, we saw before that the error depends on the double derivative, the modulus of your double derivative, divided by 12 n square. Here you have n subdivisions, so you have here, and the interval is from -2 to 0, so you have here b minus a cubed divided by 12 n square. You have n subdivision, and we found that this actually, the result here is a very accurate result, because the error does not exceed, in our way of calculating it using the trapezoidal rule, it does not exceed 6 times 10 to the minus 3, which is a very small error. If, on the contrary, you wish to calculate the number n, with which, if you choose, your error would not exceed, for example, 5, I don't remember, 5 10 to the minus 5. So what, yeah, exactly. So what you do, you use the same expression of error, except that you use here, the unknown will be n. So here you use the same expression of error, and this is the error that you want, that you prescribe. This is your prescribed error, the one that tells you the accuracy of result should not exceed an error of 5 10 to the minus 5. So you solve this expression for n, and you find that you need at least 110 points required. In other words, you have to subdivide. It tells you in order to reach an accuracy of less than 10 to the minus 5 in your result using the trapezoidal rule, then you should not take less than 110 points, and in which case you shall obtain an accuracy that would not be less, or that the error in your result would not exceed 5 10 to the minus 5. So actually, this is a very accurate way of calculating integrals when your integral concerns functions that, although they are integrable and although that they are continuous, so that you can apply the fundamental theorem, because the fundamental theorem can be applied to continuous function. But the thing is that your function, like for example the one that we saw, e to the minus x squared or sinus x squared, you don't know what kind of antiderivative, what is the antiderivative coinciding with this function. It exists, of course, according to the first fundamental theorem, but you don't know how to obtain it in the form of elementary functions so that you can apply directly the limits of integration to this antiderivative. You don't know how to obtain. So what you do, you resort to some approximate function. This is not the only approximate way of integrating it. You can use the trapezoidal rule. You can, like we did before, you can use Maclaurin expansion and you integrate term by term. There is something called the Simpson rule, and you can look into books of mathematics, simple books, to explain for you what kind of approximate methods of integration you can always have. So actually with this we come up to the end of our series of lessons, which is the application of integrals. And the most important thing is that we saw now that the fundamental theorem is so fundamental to integration, because this is all the time you use it to carry out integral, and that integrals appear in all sorts of applications, not only in economics, in engineering, in physics, in whatever, you just name it, and you find that you always meet or encounter application of integration. So integration and differentiation, when there is variation, and therefore, so actually the science of calculus is so important for a freshman student reading in any specialty or any specialization, because you always are confronted with variations. You have variations in variables, whether these variables are in economics, cost, production, manpower, change in price, these sort of applications, and whether in other, also in other sort of topics or sciences, you always are confronted with calculus. So with this, and with this, we come to the end of the series of our lessons of calculus. So, and I wish that you have had a nice time following these lessons, and that you have comprehended the main concept of calculus. And all these lessons, whereas this final one and the one that preceded, all of them are uploaded to the site of the Telematic Unin Nettuno Telematic University. And I wish you a very good luck in your study, and thank you again for the time you spent in following our lessons. So, goodbye.